Imagine you're a pollster trying to predict the outcome of an upcoming election. You're not just guessing, you're using a powerful statistical tool called a confidence interval. This tool allows you to estimate a range within which the true population proportion, in this case, the proportion of voters favoring each candidate, is likely to fall. Think of it as a safety net for your predictions. Confidence intervals provide a sense of certainty, a way to quantify the level of confidence in your predictions. But they're not just for pollsters. Confidence intervals are a vital tool in many fields, including economics, where they help forecast economic trends, in medicine, where they're used in clinical trials to assess the effectiveness of treatments, and of course, in politics, where they play a crucial role in predicting election outcomes. So, as a pollster, you'll rely on confidence intervals to make informed predictions about the election results. Now let's dive deeper into the concept of confidence interval estimation. At its core, this is about taking a sample from a larger population and using that to make educated guesses about the whole. This is where the idea of a population parameter and a sample statistic come into play. Think of the population parameter as the ultimate truth we're trying to discover. It's the average height of all people in the world, the average temperature of the Earth, or any other universal truth. Now, it's practically impossible to measure these parameters directly, so we use a sample statistic instead. This is a measurable characteristic of a small group drawn from our larger population. If we choose our sample well, this statistic should give us a good estimate of the true population parameter. Here's where things get mathematical. To estimate our confidence interval, we use a formula that involves the sample statistic, the standard error, and the z-score. The z-score is a measure of how many standard deviations an element is from the mean, while the standard error measures the accuracy of our sample statistic as an estimate of the population parameter. Lastly, we choose a level of confidence, often 95%, which means we are 95% sure that our interval contains the true population parameter. Remember, the confidence interval gives us a range within which we can be certain the true population parameter lies, according to our chosen level of confidence. So, what have we learned about confidence interval estimation? We've dived into the heart of confidence intervals, understanding how they offer a range of values within which our true population parameter likely falls. We've dissected the confidence interval formula, appreciating its mathematical elegance. Moreover, we've grappled with the concept of the level of confidence, a critical component in estimation. These concepts aren't just academic, they find utility in diverse fields, aiding in informed predictions and decisions. With this knowledge, you can now understand and use confidence intervals to make informed predictions and decisions in various fields of study.